Hello friends, this is Dharmin Patel. Welcome to the lecture series of Mathematics 2. This is the second lecture of Vector Integral Calculus. In this lecture, we will cover the work done by line integral and Green's theorem. Here, we will recall the line integral. If f bar be a vector field and r bar be a position vector of any point x0, y0, z0, then the line integral over the curve C is given by integration over C f bar dot dr bar. Now we will see the work done by force. If F bar is a force applied on the moving particle along the arc AB, where arc AB is a part of some smooth curve C, then the line integral from A to B F bar dr bar gives the work done by force applied on moving particle from A to B. Now we will see the one example of work done by force. Here f bar is given by x square minus y square plus x I caret minus 2xy plus y j caret, and a particle moves along the curve y square equal to x from point origin to 1 1. That means it is moving along the curve parabola x equal to y square from 0 0 to 1 1. Let us see how to find the work done by given force, where force is x square minus y square plus x I caret minus 2xy plus yj caret. Here work done is given by integration over C f bar dot d r bar, where r bar is x I caret plus yj caret plus z k caret. C is y square equal to x, therefore, which is a parabola. Here C is y square equal to x, parabola from 0 0 to 1 1 point. So we have to move our particle on 0 0 to 1 1 along the parabola. So 2y dy equal to dx, that is our derivative both side, and y is running from 0 to 1 along the curve x equal to y square. So our limit of y is 0 to 1. Now f bar equal to x square minus y square plus x I caret minus 2xy plus y j caret, and dr bar is dx I caret plus dy j caret plus dz k caret. Now here we have a 0 k caret which is not given in the force. Therefore f bar dot dr bar equal to x square minus y square plus x dx plus minus 2xy plus y dy, that is our f bar dot dr bar. Now we will find the directly work done by integration. Work done equal to w equal to integration over C f bar dot dr bar. Now we put the proper values of f bar, dr bar and C in the integration. Therefore w equal to integration over C x square minus y square plus x dx minus 2xy plus y dy. Therefore w equal to integration converted into the terms of y, so and y limit is 0 to 1. So we put the x equal to y square everywhere, because our curve is x equal to y square. That implies dx equal to 2y dy. Now after putting x equal to y square and dx equal to 2y, we get 2y raised to 5 minus 2y raised to 3 minus y dy. That is equal to, after taking the integration, we have a 2y raised to 6 by 6 minus 2y raised to 4 by 4 minus y square by 2, and limit of the integration is 0 to 1. After putting the limit, we have a 1 by 3 minus 1 by 2 minus 1 by 2 minus lower limit is directly 0. So after simplifying, we get the work done by force F bar is minus 2 by 3. Now we will see the important theorem of vector calculus, which is Green's theorem. In the Green's theorem, we evaluate the line integration using the double integration or multiple integration. Here mxy and nxy are continuous function of x and y, and their partial derivative del m by del y and del n by del x are also continuous in some region R of xy plane, which is bounded by some simple closed curve C. Here this is our region in xy plane which is bounded by simple closed curve C, and the line integration is given by, on simple closed curve, is integration over C f bar dr bar, which is also denoted as integration over C m dx plus n dy, and according to the Green's theorem, we can evaluate this integration like double integration over the region R del n by del x minus del m by del y dx dy. Here the double integration of Green's theorem is depends on region R, and R is bounded by simple closed curve C. And here we can apply the properties of double integration to evaluate the examples. Let us see one example of Green's theorem. Evaluate the integration over C of 2x square dy minus y square dx along the curve x square plus y square, which is our unit circle, using the Green's theorem. To solve this example, we will calculate like this. Here I equal to integration over C 2x square dy minus y square dx, and that can be written as double integration over the region R, where R is unit circle, del n by del x minus del m by del y. The coefficient of dx is m and the coefficient of dy is n. So here our m is equal to minus y square because it is a coefficient of dx, and n equal to 2x square because it is a coefficient of dy. Remember it properly. Therefore I equal to double integration over the region R. Here del n by del x is coming from 2x square, so it is 4x. It is a partial derivative of 2x square with respect to x, and del n by del y is coming from minus y square because m is minus y square, so minus 2y, which is del m by del y. So after putting the value of del n by del x and del m by del y, we have a double integration over the region R 4x minus 2y dx dy. Double integration over the region R is equal to 4x plus 2y dy dx. Here our region is whole unit circle x square plus y square equal to 1, and we are taking the only integration on the first quadrant. So here we calculate our integration to 4 times because we are taking the only first quadrant of circle. So our integration is 8 times because 2 common from 4x plus 2y over the region R. R is unit circle and we are taking the 4 times because we are taking integration only on first quadrant. So 2x, our integration is 8 into over the region R 2x plus y dy dx. Now that is equal to first integration limit is 0 to y equal to under root 1 minus x square. That means 8 integration internal limit is 0 to under root 1 minus x square and our function is 2x plus y dy. Y is the first integration and the second integration is from 0 to 1 x equal to 0 to x equal to 1. So our outer limit is x equal to 0 to x equal to 1 dx. So finally this is our integration and now we evaluate by method of double integration. So it 8 into integration 0 to 1 as it is. First we take the integration of y. So 2x y plus y square by 2. It's a first integration with respect to y and limit is 0 to under root 1 minus x square dy only dx. Here we already integrate with respect to y, so only dx is remaining. Now we find the second integration from 0 to 1, which is a only integration of x. Therefore I equal to 8 times integration 0 to 1 2x under root 1 minus x square, which is the upper limit, and plus 1 minus x square by 2. The lower limit is directly 0. So we have a now integration of x only. Now evaluate this integration. It is a single variable integration. So integration minus 2x, because we have to arrange here derivative of under root 1 minus x square. So x minus x square derivative is minus 2x arranged here. And second integration is 8 by 2 integration 0 to 1 1 minus x square dx only. Now after applying the proper formula of integration, we get minus 8 into integration of 1 minus x square raised to 3 by 2 upon 3 by 2 and limit is 0 to 1 plus 4 integration of second part is x minus x square x cube by 3 for limit 0 to 1 minus 16. After putting the properly limit, we get the 16 by 3, 8 by 3, that is equal to 24 by 3, and finally we have answer of line integration is 8 using the Green's theorem. Thank you very much.